Okay, today we're talking about motion. This is all in Chapter 2 of Beiser's book, so you can get that out if you want. It's also in the lecture notes like we talked about last time. These slides are. So motion in a straight line. The first thing that we need to know about motion is that we measure something called velocity. Velocity is simply the speed that you're traveling at and the direction you're traveling. So this is one of those vector quantities we talked about last time. If I look down and I see the speedometer says 20 miles an hour, that's a speed, right? That's just a number. There's no direction associated with the measurement on the speedometer. However, if I'm going 20 miles an hour north on I-77, then that's a vector, right? I've got my number, my magnitude, 20 miles per hour, and I've also got my direction, north. So putting the two of those would make this a vector quantity technically. Now we don't need to worry too much about that. But I think you'll agree 20 miles an hour north is different than 20 miles an hour south, or different than 30 miles an hour north, or any other thing. If I change either one of those, the whole deal changes. Velocity then, and speed, same thing, would be the distance divided by time. This makes perfect sense, right? We measure velocity in miles, unit of distance, per hour. Right? Unit of time. You could also do meters per second, feet per second, any kind of thing that uses distance over time is going to give you a velocity, or at least the magnitude, the speed. So we don't want to write velocity equals distance over time all the time. We get tired of writing out all those letters. So we simply abbreviate this thing, say V equals S over T. Like that, and that would mean the same thing as this. V is the symbol for velocity, S is the symbol for distance. I don't really know why. T is the symbol for time. And if we take those, then we're good. There's another version of the same formula, S equals VT. If you know 5 cents worth of algebra, then you know that you can multiply both sides here by T. If I put a T right there and multiply it, it would cancel it here, but I'd also have to do that on the other side. And I'd end up with a VT equals S. Flip it around and you got this. So here's a second version. Maybe they say you're going 40 miles an hour and you do that for 3 hours. How far did you get? Well, 40 times 3 would be 120 miles. And so this formula kind of holds with common sense there. Here's time is distance over velocity. A third version of it. Again, algebra comes to the rescue. If we divide both sides by V, you can see that we'd end up with this real quickly. So there's 3 different ways to do it. In this class, pretty much if you can pick the right formula and put the numbers into it, then you're fine. Okay? We're not really trying to do fancy stuff with math. On the first 2 tests, you're allowed to bring an index card to the test, a little 3x5 index card. Right, 3 inches by 5 inches. So you can put formulas on there, examples, whatever. This might be something that you want on there. And then if they gave you a problem that said, here's how many miles you went in so much time, what's the velocity? You could pick that one up. Or if they gave you velocity and time, you could get the distance. And if they gave you distance and velocity, you're going 100 miles, you're traveling 50 miles an hour, how long is it going to take you? So that kind of thing. Here's some examples where you can see what it might actually look like and start thinking about how to format that card and your what's going on here. The first one here, if a person walks 15 miles in 3 hours, what's the average velocity? Okay, all the problems look kind of like this. We usually call them word problems, and some people get scared of that, but there's nothing to be scared of here. All you're going to do is you're going to read the problem. You're looking for numbers. Right there, ding, here's a number, 15 miles. And you know that's a distance. So you may want to come over on the side of your paper and scribble S equals 15 miles. That way you've got the number stored, and it's also already assigned to the variable that it belongs to. Right here, 3 hours, right? That's a time. We measure time in hours. Just look at the unit and say, well, hours measures time. And you got it. Okay, nothing tricky here. What's the average velocity? They want the velocity. So I look at my formula sheet. I got V equals ST. I got S equals VT. I got, they want velocity, so pick the one that's solved for velocity. I got this one. I got that one. I put the numbers in, divide. 5 miles per hour. Okay. Number 2 here, if a car travels at a velocity of 2 meters per second for 30 seconds, how far did it go? Again, read the question. Looking for numbers right there. 2 meters per second. I see the unit meters per second. I know that's a velocity. They also told me here. So that's V. V equals 2 meters per second. 30 seconds would measure time. So I put T equals 30 seconds. How far did it go? I'm looking for S. I get the formula that starts off with S. I put in V, I put in T, and I've got my answer. Okay, 60 meters. If I travel 175 miles at 70 miles per hour, how long will it take? Right there, distance, 175 miles. That's S. S equals 175 miles. 70 miles per hour. I know miles per hour measures velocity, so I put that down. V equals 70 miles per hour. I've got a formula that says time equals distance over velocity. I put in my numbers, I get my answer. Easy as pie. It's a good thing to do to kind of watch the units. Right here you see I've got miles over hours, so I end up with miles per hour. Right here I have meters per second times seconds. See how these seconds and those seconds are going to cancel? So I end up in meters. The only unit left is that M right there. This one's a little bit trickier. You got miles over miles per hour. So I'm dividing by a fraction here. You may remember that when you divide by a fraction, you have to invert and multiply. So if I flip this thing upside down and multiply, then I'd have miles times hour per mile. So I got a mile on top, a mile on the bottom. Those are going to cancel out. I'm left in hours. It's right there. It does work out. It's nice to watch those and understand what's happening. It's not essential, but it certainly ensures that you get the right answer. Number 4, if a plane travels north at 120 miles per hour for 3 hours and then turns and flies west at 100 miles for 2 hours, how far away from its starting point is there? Now, I got to warn you, there is a typo in this problem. See if you can find it. We're going to travel north 120 miles per hour for 3 hours. That would actually take me 360 miles, wouldn't it? So the first side of this thing, I'm flying up along, we could imagine this being the north passage that my plane's flying right there. 360 miles along that side. Then I fly and turn west. So I'm going that way. 100 miles per hour for 2 hours would take me 200 miles. Somehow I put the number 100 right here. Okay, so that really should say 200. But you can see the triangle part, right? I go up, I go over, and what I want to know is how far is it from here to over where I ended up. The Pythagorean theorem will do that. We talked about that last time, and so there's a good application of that. Acceleration. Acceleration is an idea that says we can change our speed. We don't have to go the same speed all the time. So if I'm going 2 miles an hour and then I speed up to 8 miles an hour, there was a change in speed there. So what we do when we look at this formula, A, the acceleration, equals V, the velocity, minus V naught. See how I have two different velocities? I've got the one at the beginning, 2 I think we said a minute ago, and the one at the end, I think we did 8 or something. There's 2 numbers there, 2 velocities, so somehow I have to differentiate between those. You could call them V1 and V2 or anything else you like, but the way our book does, and this is what most books do, is they will come along and they will say, all right, V is going to be the final velocity, and V naught, that little 0 right there, says that at time equals 0, at the beginning of the problem, here's my velocity. This would be the velocity at the end of the problem. Okay, so just a little bit of notation there, but it's a handy little formula. I want to take the change in velocity and divide by the time. How long did it take me to go from this speed to that speed? And that number is my acceleration. So that's a good definition. We'll do some problems with that in just a second here. But let's look at these other 2 formulas. Right here, distance equals velocity times time plus 1/2 AT squared. I won't work that out for you. It involves, well, there's 2 ways to do it. One's a whole bunch of algebra, one's a little bit of calculus. So I don't think you want to see either one of those. But if you'll take my word for it that this formula works, then it's a nice formula. Just on a common sense kind of thing, say I'm going some velocity for a period of time, that would take me a certain distance, wouldn't it? But if I'm accelerating for some time, that's going to take me some more distance because I'm going faster than I was before. So if I want to know my total distance that I traveled, S, I'd have to take that distance that I would have traveled at the first speed and add the distance that I traveled because I'm speeding up. That'll give me S, the total distance. It's a nice formula. Right here, the last one on this page, the final velocity is equal to the initial velocity plus the acceleration times the time. I'm going one speed. I speed up for a certain amount of time. That's going to make me go faster. If I add those two, I get the total velocity. This is actually another version of this same formula here. A little bit of algebra will turn this into that. Okay, but these three formulas here are kind of the foundation for understanding how things move and how the distance and the velocity and the time and the acceleration, how all of that relates together, and gives us a nice framework to solve these kinds of problems with. There's one other number here that you should know about: acceleration due to gravity. When we drop an object, then gravity works on it. The Earth's mass exerts a force on that, and it pulls. And this acceleration, that speeding up because of the gravity of the Earth pulling it, is equal to 9.8 meters per second squared, or it's also 32 feet per second squared. Same measurement, it's just different units, right? This one's in meters and that one's in feet. But if I drop an object every second, it's going to be going 9.8 meters per second faster than it was the second before. Every second it speeds up 32 feet per second. Okay, so that's an important number that we'll see again. Let's do some example problems here. Number 5, if my car is stopped at a light and then speeds up to 4 meters per second, in 2 seconds find the acceleration. Okay, looking for acceleration, so we whip out the acceleration formula right there. I'm looking for V, V naught, and T. And I go through my problem. If my car is stopped, do you see that? Did you see that right there? At the beginning of the problem, the car's velocity is 0. So you could scribble on the side of your paper, V naught equals 0. That is stopped, means V naught is 0. It then speeds up to 4 meters per second. Another number there. 4 meters per second would be the final velocity. And 2 seconds is how long it takes to do that. That's clearly the time. So we've got all our numbers, right? V naught was 0, V is 4, and the time down here on the bottom is 2. So I'll go 4 minus 0 is 4. Divide that by 2 would be 2. 2 meters per second squared are the standard units on this thing. I think you can see that we'd end up with meters per second on the top. I'm dividing that by seconds. It's not wrong to say meter per second, but here again, if we invert and multiply, then the units work out looking like this. That's the way we prefer to write units of acceleration. Here's another one, same deal. The numbers are a little bit different. If I'm traveling 6 meters per second at the beginning of the problem, V naught, I get 6 meters per second. I'm going to step on the brakes to slow down to 2 meters per second. At the end of the problem, the second speed is 2 meters per second. It takes me 8 seconds to do that. So I put the numbers in there. I started out at 6. I slow down to 2. My final is 2. 2 minus 6 would be negative 4. Divide negative 4 by 8, you get negative 0.5. The difference here is I'm slowing down. So my acceleration vector points in the opposite direction. There's a negative sign there that says opposite direction. The other way, you're slowing down, whatever way you want to think about that. Okay. There are some other things that we can do with those other two formulas I showed you. Here, for example, a falling object. We talk about free fall. And if I just drop an object, if I just hold it out over a building like it says here, I drop a rock from the top of a building, then how far will it fall? How fast will it be moving? Those kinds of questions. How long will it take to hit the ground? All of those questions we can answer with physics. If I want to know the velocity, then I get the velocity formula. I say, well, how fast was it traveling when it left my hand? If I just open my hand and drop it, then the initial velocity is 0. So we've gone ahead and put that in here. Gravity accelerates it. So that would be 9.8 meters per second. And we're going to put in here whatever time it is. So see how they say after 1 second, how fast is it going? After 2 seconds, after 3 seconds, after 4 seconds. And I think you can see the numbers are already punched up here, meaning that after 1 second, it's going 9.8 meters per second. That is 9.8 meters per second faster than it was going at 0 time, right? And then after another second, it's going 19.6, which is 9.8 faster than it was before. After 3 seconds, it's moving 29.4 meters per second, 39.2 meters per second. It's just speeding up, 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 up. Now, in real life, you do have something called air resistance. If you take a sheet of paper and you drop the sheet of paper, it just slowly floats to the ground, right? Whereas if you ball it up, if you wad that piece of paper up and drop it, it falls a lot faster. The air pushes back on the falling object. We're not going to do air resistance. We're not going to play with that. You can build a formula and you can account for that. It's not hard to do, but we will just totally ignore air resistance. All right. So what about the distance? Well, if I get the distance formula, I know the rock was initially traveling 0 because I just opened up my fingers and let it fall. I'm going to put in however long, but 0 times anything is 0, so I really don't need to worry about this first term anymore. Over here, 1/2 AT squared. 1/2, the acceleration is gravity. There's the time. So as I put in 1 second, 2 seconds, 3 seconds, 4 seconds into time right there, I'm going to get these numbers. And look at the distance this thing travels. In the first second, it only travels 4.9 meters. That's pretty good, but that's what, the height of 2 people, maybe 3 people. So right here, after 2 seconds, it's traveled almost 20 meters. After 3 seconds, it's 44 meters. After 4 seconds, 784 meters. This thing really picks up speed. It's because of that t squared term right there, where the time is being squared, and I'm multiplying it twice there. So it makes a big jump. All right, those are some of the basic formulas from physics. I got some more, but those will be in the Chapter 3 video, and I hope you have a good day.